Right, so in this video, we just have 2 weeks left of limits, and what we're going to try to do is still talk about continuity of functions in a sense. We're going to do that by looking at what we call removable discontinuities in more detail. So what you should know from our last videos is that a removable discontinuity is a discontinuity that's a whole. Now what does that really mean? It means there's some wacky looking function where the left hand and right hand limit agree. So in other words, the general limit exists, but the actual function value is undefined, or maybe just isn't what that limit value is. Now the question is, how can we fill this hole? And so I'm going to take an approach that you can't really use on this assignment. I'm going to first go to Desmos, and you can use it, but this is obviously not the preferred way of doing it. What I'm going to do is I'm going to write that function in, because again, there is a removable discontinuity. There is a graph with a hole. We just don't see it necessarily. So let me get this function in there. Okay, so here's the function, and whoops, if I zoom out, I mean, obviously there's nothing going on over here, but the question is what's going on at x equals 3. All right, that's where the breakpoint is. So obviously this function isn't defined for anything less than negative 13. We see that clearly. It's defined at negative 13 exactly. You get 4, and so on and so forth. But at x equals 3, oops, already passed it. So at x equals 3, it says it's undefined. Now the thing is, understanding how limits work, we can see that it looks like at 3, the limit should be 8. Or in other words, what should be going on here is 8. If I wasn't clicking on this, you would just think, oh, everything's fine. At 3, evidently the function is 8. But that's totally missing. So the question is, how do we figure out that it is 8? And actually, the answer is we do what you've done on a prior Khan Academy assignment. So long story short, here's my explanation. What on earth is this whole crazy structure saying or doing? It's saying here's a function. It's not allowed to have negative 3 plugged into it. Why not? Well, because you get this hole in it. The question is, what value does the hole need to have this circle filled? The value is 8. So at 3, it should be 8. So the answer for k is 8. But let's see how we get that. And again, we're actually just reviewing something we did before. So how on earth did they figure out that 8 is what fills this? Well, this is a limit using conjugates. So what do you do for limits using conjugates? I think we saw this last week or 2 weeks ago. You multiply the numerator and denominator by the conjugate of the term that involves the square root. So in other words, conjugate means switch the sign in between. And obviously the term with the root is that one with the root of x plus 13 and the 4. So notice I'm switching that minus in between the root and the 4. And let's multiply by the conjugate. Let's see what happens here. When we do this, again, never FOIL out the non-conjugate pairs. So we're just going to write that as x minus 3 the original. Now I'm going to FOIL out the bottom. Be careful when you do this. The root times the root is just the contents without the root because it's identical. Put it in parentheses though. You might need to distribute a negative if it were on the back end instead of the leading term. The middle terms are going to cancel out. I'm going to skip that because you've seen this from prior weeks. And then we're going to have negative 4 times 4, which will be negative 16. Okay, so if you notice, I'm going to skip some work here. X plus 13 minus 16 is really just x minus 3. Okay, so these cancel out. So we just get, actually this whole thing over 1, so we just get this. So the question is, what is the limit as x approaches 3 as we approach this? Now again, you should be there. There's a little bit of different notation if you move on to calculus. You're supposed to actually carry the limit symbol after every equal sign, so just know that. But from there, you can see if you plug 3 into this, you get the root of 13, or sorry, the root of 16, which is 4. So we really just have 4 plus 4, so we get 8. The same thing I've been saying all along. Okay, so in other words, there's a hole in this graph. The hole is at 3. What is everything around that hole leading up to? 8. So what value fills this hole, therefore making this function continuous? 8. So you're finding what was removed and essentially refilling it. So it's a lot of weird, wacky notation that you don't necessarily have to understand unless you feel like going on to calculus. If you plan on doing that, hopefully you understand the nature of piecewise functions and what's going on here. But all you're really doing is saying, if this says 8, I'm filling the hole that's missing in the graph. So I'm going to get away from Desmos now and now just complete these what we call algebraically. Ooh, I hope I'm recording with the audio because I heard that out loud. 1 second. Okay, so now I have a different function. And so it's saying essentially the same idea. What should we plug in when we plug in, what should we get when we plug in 0? Now the thing is, and we've seen this before, if you were to plug in 0, you would get 0 over 0, trust me. And that's what we call indeterminate form. So we're going to figure out, well, what should we be getting as we approach 0? Now the way you do that in this question is you factor stuff. Now what you notice is every single term in this problem has an x, or what you should notice is every term in this problem has an x. So you can actually factor out an x. You'd just be left with 10. You'd be left with x squared, and you'd just be left with 5. So now let's try plugging in 0 to this. Well, when I plug in 0 to this, I get 10 over 5. Well, what's that? That's 2. So what fills the hole? 2. All right. Moving right along, we have another conjugate question, so I'm just going to dive into that conjugate process. Keep the non-root term. Well, really, I'm just copying the whole problem. All right, so I'm going to multiply by the conjugate of the term that involves the square root. Switch the sign in the middle, that's what a conjugate is. And leave the non-conjugate terms undistributed. And FOIL out the conjugate pairs. Make sure you write what's in the root in parentheses just in case it's on the back end again, and we get this. So same as last time, this simplifies to x minus 2, so x minus 2 and x minus 2 cancel out. So we're really just left with x plus 7 plus 3. Oops, plus 3. So what is the limit if we approach 2 of this? Well, plug in 2. 2 plus 7 is 9. The root of 9 is 3. 3 plus 3 is 6. And we've got one more. Ooh, this one's special. Okay, this one is definitely a little bit difficult to see at first what you need to do. But this term, or this, function, in the denominator has a common term, and the common term is e to the x. This takes a while to see, but you can actually factor out e to the x from the denominator, and you would be left with x plus 1. I mean, redistribute this, you would get e to the x in an x, which is what we have right here, and then you would just get, well, anything times 1 is itself, so you would get plus e to the x, and so there it is. So once you realize that the e to the x cancels out, well, look what we have. We have x plus 1 on the top, and we have a factor of x plus 1 on the bottom, so those cancel out. We're left with 1 over e to the x. The question is, what is the limit as we plug in negative 1? Now this is, again, going to be a little bit fancy. The limit as we approach negative 1 of 1 over e to the x is really 1 over e to the negative 1. And there's one special rule going on here. If you have a negative exponent, it's allowed to flip to the other side of the fraction and become a positive exponent. So in other words, a negative exponent on the bottom is a positive exponent on top. Anything to the first power is itself. And that's it. So hopefully that helps you get through this assignment. It looks like you're going to be seeing a lot of factoring and conjugates going on here. Good luck.